Okay, all right, maybe we'll start talking again. You guys are good sports. I know today's been heavy, right? So we've done a lot of heavy lifting, looking at things, lots of linear algebra, lots of triangle inequality. As such, we'll try to make, we probably won't go the full time with this last one. I'll probably keep this to like 25 minutes or something. We will have one more very challenging lecture in this series, the first one tomorrow. The reason is like I think with what we're going to talk about now, you might consider a supplement. But I think with the last two lectures and the lecture that we'll have first hour tomorrow, I think in some sense they really formed the foundation for kind of like why sparse recovery works. So what we're going to do tomorrow morning is, a lot of you asked, what we're going to do tomorrow morning is to talk about why random matrices have this restricted isometry property, and for what what kind of aspect ratios they have. So, some very astute students came up and asked me, it's like, okay, well, we wrote all this stuff on the board about when you can recover a sparse vector using L1 minimization, but I didn't see M anywhere. Where's the number of rows in the matrix? Like, why isn't that playing a role in what we're talking about? But it does play a role, right? It's just hidden. We've sort of made this dichotomy. So, where M plays a role is like, sort of the assumptions we made here was, if we said that if this matrix phi had this restricted isometry property for 3s sparse vectors, then all this other stuff was true. Right, and so where M comes into play is like actually showing that matrix phi has that restricted isometry property. So that's where that comes in. So it's because we made this division between the random and the kind of deterministic, or in this case, the kind of geometrical and linear algebraic properties, and these properties of random matrices. They're kind of two aspects to the mathematics of what's going on here. Okay, so that's where that M starts to come into play, and that will be in sharp relief in our first lecture tomorrow. Okay, and then also the other place. So the first part of the lecture today, we talked about these different kinds of like duality conditions. So these dual certificates and such. And then there M plays the role, and we saw in kind of our example, like plays the role. It's like, oh, when is the matrix invertible? Well, it has to have have to have appropriate number of rows versus columns. And also, like, how do I bound the norms of these vectors after I apply Cauchy-Schwarz? That's also where the kind of number of measurements comes into play. Okay, so let me sort of re-summarize what we did last hour, simply because it's gonna make it a nice starting point for what we do now. So here's kind of what we said. We said, okay. Granted this matrix has a special property, we kind of set up these two things. We said, okay, look, we look at min x L1 subject to phi x equals 1. And kind of what we did is we said, okay, let's look at point x naught. So it's kind of like we looked at our given vector x naught, and we said, okay, if we add a vector h to this, does it decrease the L1 norm? Right? And so vectors h which do decrease the L1 norm we call descent vectors. Right? And so then we also ask, if to stay feasible, we also say that phi h, is equal to 0. Okay, so then we sort of ask, like, are these two things compatible with one another? Can I descend in the L1 norm, make the L1 norm smaller while staying in the null space? Right, and so one thing we said was kind of a purely geometric condition. We said, okay, look, if you do have a descent vector, if this is true, then it has to be true. No matter if, this nothing to do with the matrix phi, then it has to be true that if I look at the L1 norm on the support, it has to be greater than this L1 norm off the support. Right? Because this is kind of just, nothing didn't have anything to do with any matrix. We said, all vectors H from a point x naught, all vectors H which decrease the L1 norm, they have to have this kind of geometrical property. They have to be, in some sense, more concentrated on the support of phi naught than off the support. And then what we said was, look, that was completely at odds, if phi has this restricted isometry property, completely at odds with phi h being equal to 0. Right? Because what does the restricted isometry property says? It kind of says, like, okay, I preserve the energy of all sort of sparse vectors. And then, roughly what you're saying is, like, for me to not to preserve the energy, stuff kind of needs to be spread out. Right? In some sense, since this is for me, or for me to be in the null space, stuff kind of has to be spread out. It can't be sparse. Right? So what we said is this idea of things being, not exactly concentrated, but concentrated like this, and this idea that, I have to be kind of spread out to be in the null space, those are, again, we're kind of at direct odds with one another. Okay, so that was good. And what's another sort of nice thing about talking about things in this manner is we can sort of begin to very easily talk about stability, right? And so, and let me just motivate this real quickly. So let's put it up real clear why this, we might want to do something like this. So we looked a lot at, like, yesterday, I've shown you this picture lots of times. This picture of Pau Gasol, right? So here he is. And, what we would kind of argue about is, like, let me see. Sorry, let me look at something else. Actually, look at the first day. Okay, well, anyway, let me, sorry about that. So anyway, the idea here is, like, when I look in the the wavelet domain and I say, okay, look, these signals, they get concentrated onto a small set. That's good, but, like, nothing here is exactly sparse, right? Whenever we're talking like this, we always, even if we don't have any noise in our measurement system, we sort of in the wild never have signals that are exactly sparse, or let's say it's rarely the case that we deal with signals that are exactly sparse. So particularly in imaging, when I say things like, this isn't really a megapixel, it's more like 40,000 wavelet coefficients. It's not exactly 40,000 wavelet coefficients. It really takes, a million wavelet coefficients to exactly build up this picture back. But the idea is I get a very good approximation with 40,000 wavelet coefficients. Okay, so, what I'd really like is I'd like things to be stable in the presence of this sort of modeling it. The fact that, when I actually write y equals phi x naught, I can't reasonably expect x naught to be exactly as sparse. Just like, when I sample a signal, I can't reasonably expect that signal to be exactly bandlimited, right? But I can talk very intelligently about the errors I incur if it's not bandlimited, right? Things alias back, I can integrate the tail, talk about what the error will be. So we want to do the same thing with this idea of L1 recovery. Now, our task is a bit more arduous in the sense that, again, this procedure is completely nonlinear, right? So we analyze sampling. So if something's not exactly band limited and we sample it too slowly, we know really well that error kind of folds back in. And because the reconstruction is linear, we can talk, very, very easily about what the size of that error might be. So here we have, like, very nonlinear reconstruction thing, right? It's like as I change y, of course the as I change y, the solution to this changes nonlinearly as I change y. But I could say that, like, if those changes in y are caused by adding arbitrary small values to x, and sucking it through this matrix phi, I can actually bound them or control them very nicely. Okay, so that's exactly what I want to do. So actually, I say we have 3 essential results here. Really, in the notes, we only have the first 2. So the last 3, it's kind of, I was going to do 3, but it's by this point, it's going to become more of the same. So I think if we look at the first 2, it'll be enough. Okay, so here's the idea. So we'll say again, we have this vector x naught, and now we'll have the case where we measure this y equals phi x naught, but x naught's not exactly S sparse. So in some sense, we can't expect the solution of this to be exact anymore. In fact, we're not going to make that guarantee, and in some sense, it can't be true. But what we're going to say is okay, look, now we're going to look at this difference between the solution to this program. The solution to the program is something. We'll call it x sharp. We'll look at the difference between this. Forgot to put this on. Look at the difference between the solution and the true underlying vector, and we're going to control the size of the difference between these 2 things. And we'll control them in 2 ways. One is we'll control it, we'll say if x naught is not sparse, we can bound the 1 norm of h. We can also bound the 2 norm of h. And actually, this result uses the first result in kind of a tricky way. So we can talk about, this result will come quickly, and you kind of sense it'll be nice since the 1 norm appears in the recovery and the 1 norm appears in the result. We might be more interested in things like mean square error. We usually measure errors in this 2 norm, so it's nice to also control the 2 norm of this vector h, and we can talk about that as well. And then, there's another way we can talk about things is say when x naught is sparse and you have, say, some error, arbitrary error in the measurement, what can I say then? And it turns out you can also make the case that this is stable. We won't today, but the arguments are similar but different than what we do. And you can also say, if it's not sparse and there is noise in measurements, you can also get the result simply by actually really just combining these results. Okay, so now the question is what changes about this argument that we had before, right? And so again, what our essential argument before was if I had something which decreased the L1 norm of x, and we had this geometrical condition on it, and you sort of showed it was incompatible with this. Now what we'll show is since x naught is not exactly sparse, this won't be exactly true. So we just have to adjust for that case. And what happens when we adjust for it? What we'll see, what kind of pops up is, again, we won't be able to do this recovery perfectly. Right? But what we can say is we can actually say something pretty nice. We say, okay, look, at the end of the day, the thing we get out, it's not exactly x naught, right? But I can talk about it being almost as good as x naught as the best S-term approximation. Right? So in some sense, I have exactly the same set of conditions. So now phi is a matrix which obeys this, this restricted isometry property for vectors which are 3S sparse, right? And what that says is, okay, look, if x naught was exactly S sparse, I could recover it exactly. What would be sort of in a perfect world that say, okay, now x naught is not exactly S sparse, I can recover something as good as the best S-term approximation, right? And so that would be, say, I could recover the biggest S terms in x naught and just give up and set everything else equal to 0. So what I denote is that as x0s. So what this is since x naught is exactly, since x naught is not exactly S sparse, what this is basically the best S-term approximation, which is basically, I just take x naught and I look to keep its S biggest terms and set everything else equal to 0. Right, but what this says is okay, look, I don't recover exactly that, but I recover something almost as good as that. So actually this C delta, you can control. It can be small. It can be on the order of 2 or 3. So it means I'm not giving up much here. Okay, so that's what we're going to just sort of talk about for the next 20 minutes or so. Is what this is true, and can I do something similar in the 2? Okay, So the argument has much the same tenor, so we can actually skip a lot of it or move quickly through a lot of it, because even if you don't remember it exactly from the last lecture, like the sort of general themes are the same. So here's what's sort of the main condition, the main thing that changes. So what changes is now, this cone constraint, this idea that, let me write this down. We have this sort of idea that if I had a sparse vector, so here in this case it's a vector on the axis. Well, it's not even draw this. Forget about this subspace. Let's make this bigger too. So the idea was, how I got this constraint first. Okay, let's let x naught be something at one of these facets. So in some sense, it's it's at a point here. So this is a sparse vector, and then we saw that look as if I look at vectors h to add to x naught, which lower the L1 norm, I have this condition on h that its L1 norm on the support had to be bigger than its L1 norm off the support. Right, so this is true if I'm there. That's how what constrains the fact that x naught is exactly at this point is what constrains the sort of range of values h can take like that. Okay, so now, what we're interested in now is like, what if I don't have this situation, but x naught is kind of like almost sparse. Right, so what does that mean? Like x naught is like, say, over here. Right, now it's like, okay, for small h, I can move in almost any direction in this half plane. Right, but for large h, I can't move too far in that direction. I can move a long way here, right, and I can move a long way like this. Right, and so what kind of a property that captures that is, we can come up with sort of this modified cone constraint that says, okay, look, if x naught is almost sparse, I can only move a little bit, I can move basically in every direction for small steps, but for big steps, I can only move a little bit in some directions and still move a long way in other directions. Okay, so how do we formalize something like this? It's almost exactly the same. So we take, here's x naught plus h, we look at its L1 norm. We know that this L1 norm has to, so again, h is the difference between the solution and this true vector x naught. So we know that this L1 norm has to be less than the L1 norm of x naught, just because we know that both x sharp and x naught are feasible, and by definition, x sharp is the feasible vector with smallest L1 norm. Okay, so we do the same thing. So you look at this thing, you separate it onto sum of terms on the support, sum of terms off the support. And then, again, I just simply kind of apply this reverse triangle inequality. So if I have the sum of the absolute value of two numbers, that's greater than or equal to the difference of their absolute values. And that's true in both of these cases. And it doesn't matter which order you take the absolute values, the greater than or equal to is always true. Right? And so then, what we have here is we just have this statement that if I look at, if I have a descent vector h, which lowers the L1 norm of x naught, right? What I can say is the L1 norm of x naught plus h. It's equal to the L1 norm of x naught plus the difference between these L1 norms on the support of h. So that is sort of essentially exactly what we had in the case where x naught was exactly sparse. But then I just have this additional term. So I just have twice sort of the sum of the values of x naught off the support. Right, so everything proceeded in exactly the same way, except for I still have this sort of straggling thing. I have these x naughts that are appearing in this side of the sum. And so I just incorporate that in. So this says, like, look, what is this? This is basically, if I define gamma naught now as being the locations, not where x naught is non-zero, but the locations of the s largest x naught. This is just, the L1 norm of the difference between x and its best s-term approximation. Okay, so that becomes my new my new sort of geometrical constraint. So the idea, if I have an x naught which is approximately sparse, the constraints that you put on h is that if I look at the kind of L1 norm off the support of outside of the locations of these S biggest terms, it doesn't have to be less than the L1 norm on the support, but rather less than norm plus the twice the difference in this approximation. So again, it's the fact that x naught is only approximately sparse. It just comes up in this way when we talk about we haven't talked anything about phi yet. But this is just the geometrical encoding of, what do I need to add to a vector x naught to decrease its L1 norm? Well, this is a property I must have. Okay, and so that's one fact. So here's the one fact we have. Another fact that we have, we know already, is from our last proof, is we already showed that if phi has this 2s rip, right, then we know that we have this opposite thing that's true. So if H is in the null space, which again it must be, since we're solving this program with the same constraint, we know that this on the support has to be less than rho times the L1 norm off the support. This is what we showed in the entirety of the last lecture. So if I can just combine these two things, right, it's kind of easy. So I have these two facts about the descent vector. All right, so the first one, just plugging this up here. All right, so I have where's my pointer? So I have that, I know that this is true. I also know by plugging this in up here, right? I also know that I have I can arrive at this. All right, so basically I know that the L1 norm of H gamma naught C off the support, I can bound that by some constant times the difference in the area. Right, but now I sort of have everything. So now I can say, okay, what is the L1 norm of this error, right? Since that's all this is just the difference between the true solution, the actual solution of the optimization program, and the thing that I'm trying to recover, my sort of ideal solution. I can just add these two things together. Right, so since these are disjoint supports, the L1 norm of their sum is the same as the sum of their L1 norms, and that's what you get. Right, so basically the difference between what I recover and what I'm after, the non-sparse vector, it's again just simply by using the work we did before to show this, right, and this new cone constraint, just combining those two things almost immediately gives that, the L1 norm here is less than the L1 norm of this difference, again, times some constant. So again, this constant, if rho is less than 1, say rho is less than a half, then, this turns out to be something like 6 or something like that. Okay, so that's easy. So that's one nice result that follows almost immediately. All we did was say, okay, we have this new condition, which is again just the triangle inequality, just codifies this kind of crude diagram on the board. And we did all this work from last time, and now we just sort of add these two things together. And we get the stability in L1. Okay, so that's good. So we might write that down. But we look at basically this x sharp minus x naught in one norm is less than 2. 1 plus rho, or 1 minus rho. X naught minus x0. Best S term approximation. Okay. Good. So that's good. And that's that's heartening because it's so much simpler than what we did before. This only took if you cut out all my commentary, you'd probably go through that in 90 seconds. Okay, that's good. So now let's talk about how might we get a 2-norm result. All right. So in some sense, what we've done right now is show this 1-norm result. So that the recovery error measured in the L1 norm is the same within a constant as kind of the best approximation error, also measured in the L1 norm. So what we'd like to do is at least change this left-hand side. Is can we get an L2 stability result? Because that's what we're used to. When I do recovery, I say okay, I apply this pseudo-inverse to a noisy set of noisy measurements, and I ask, how good is the result? Well, I always answer that question in terms of the 2 norm, right? Because that's kind of what goes hand in hand with classical linear algebra. So I'd like to do that here as well, too. So all you need to do is like a little more manipulation of this, and you can turn, basically the left-hand side also into a 2 norm. So here's essentially how the story goes, and you need to take one other key result from what we did before. Okay, so here's how it goes. So what we say is okay, look, we're interested, not necessarily in the 1 norm now, now we're interested in the 2 norm of this vector. And again, if I have the same definition of these sets, gamma naught and gamma 1, right? So now gamma naught is the size. If I have a fixed vector in the null space H, or in particular for this fixed vector, which we know is in the null space, what I do is I just say, okay, gamma naught is the set of locations of the S largest entries in X naught. Gamma 1 is the set of entries that are the 2S largest outside of gamma naught entries in H, etc. Gamma 2, gamma 3, all that. And then, what we do is say, okay, let's look at the norm of H squared. What I do is I just break it into 2 parts. One on this sort of union of supports, gamma naught and gamma 1. So that's kind of like, the big part of X and the big part of this vector H, the big part of the difference between these two. And then everything outside of the support on H. And then it turns out that, this first part we actually got a bound for in the last lecture. So let's just go back in the time machine here. And look right here. So at one point here we had this written on the board. So if I looked at, what H looked like, I looked at it to say I just square both of this. I get some constant times, the L1 norm of H off the support over 2S. And again, this is basically, I got to this result just by taking the fact that H was in the null space, and I applied this restricted isometry property and then the triangle property a bunch of times. So that's all we say there. So. Right, so I have this result from last time. I already kind of shown that in some sense, H being in the null space, what that means is it means the 2 norm on this support, like, kind of where X naught is big and kind of where H, the other terms in H are kind of big. This has to be less than, something to do with the L1 norm squared, on the rest of this support. So we kind of showed this already. So now we can say, okay, look, in some sense I have a bound with what to do with this first term. What to do with the second term, we just need a few manipulations. Right? So here's what we do. We say, okay, look, here's one little trick I can play. So it's like if I look at what's going on here, this is sort of the sum of the absolute values in gamma naught C of H. So what's one thing I can replace that by? I say, okay, look, if I could rewrite this as the sum over all entries in K. Right? I can say, like, look, if I look at the K largest term here, I can bound that by the average of the K largest terms. Right? So all that's bound is saying, like, if I have a sequence of numbers which looks like this. So here's the 4th largest. Right? This is necessarily less than the average of these 4, just from the way I've ordered things, which is necessarily less than 1 over K times the sum of all of them. Okay, so then how do I sort of use that fact? Well, I say, okay, look, what I can do is if I look at what's going on in the rest of this, I can say, okay, let's look at this second term. Let's look at each entry, right? And I can sort them and talk about just summing them in order of how big they are. And again, what I can do is say, okay, look, I can replace this K largest entry with, again, this L1 norm squared over K squared. Right? So then this is the sum from K equals 2S plus 1 to N. Right? I can simply use the fact that the sum of 1 over K squared for, this goes from K equals 2S plus 1 to n, but say from k is greater than 2s plus 1 to infinity, 1 over k squared is less than 2s, I mean, I can just replace this basically with the L1 norm of finite gamma c squared divided by 2n. And so basically it's just, again, a simple manipulation to make something out of the second term and relate it to the L1 norm of h off the support. So that's what I get. So now I just combine these two things. Right? So I say, okay, look, what's the 2 norm? Take the h squared. So I have a bound for what goes on the support. I have a bound for what goes on off this augmented support. This thing looked like 1 over 2s times the L1 norm off the support that I had from my previous work. This just followed from this, simple argument here. And so what do I get when I do this? Well, this is good. I mean, what I can essentially say is that, the difference in the 2 norm between what I recover and what I'm after, it's some constant over 2s times, this h gamma naught c. But what was h? H was exactly this. It was the difference between the solution of the optimization program and the vector that I'm trying to recover. Right. So again, this is just exactly the difference in the difference between x naught and its best S term approximation. And again, that difference is in the 1 norm, but it's squared. But kind of the difference here is divided by x. Right. And so I can sort of collect this all in the end of the day to say, look, the difference in the 2 norm between these two things. What I can do is I can bound it. I don't bound it in terms of the 2 norm of the best of x naught approximation. Right? Maybe that's a little off-putting. I can bound it in terms of the 1 norm, but I actually get something back. I actually get back a factor of square root of x. So of course, the L1 norm is bigger than the L2 norm, right? But I also get back this factor of square root of x. So that's something. Okay. So what do we have, right? So we showed just by doing some kind of simple manipulations, right, that even if my vector x naught is not exactly sparse, I can have two almost very easy results given what stuff that I've done so far. So one is if I'm just interested in bounding this L1 stability, so the L difference in L1 between what I recover and my vector which is not as sparse. It's some small constant, which again just depends on these restricted isometry constants of this matrix phi, times kind of the best I can do, the best S-term approximation. All right, and if I'm interested in the 2 norm between these two different things, again what I can do is I can bound it, not in terms of the 2 norm between the best S-term approximation, but something which is almost as good. I can do the 1 norm between these two things, but then divided by the square root of x. Okay, so that's what we sort of have to say about stability. It is true. I mean, that we can, if I were to continue on for another half hour, this is what I do next. I'll kind of spare you because the main ideas are all there. It's just sort of more manipulations. And what you can also say though is let's say that x naught is sparse, but I add an arbitrary measurement noise. Right, then you can say, look, I'm not going to be able to recover x naught exactly. And in fact, let me not even bother trying to match the measurements exactly. Let me relax them so that this 2 norm is less than epsilon. Then you can actually, using again these ideas of a geometrical constraint on a descent vector, and the fact that you have to be in near the null space, you're not exactly in the null space now, but close to the null space, and phi has this restricted isometry property. You show that the difference between what you recover and your original signal is on the order of the noise level epsilon. Right? So exactly like recovering from an ortho system. And that's fine. And then you can also mix these two. So you can say if x naught's only approximately as sparse and I add noise to the measurements, I can just add these two results together. So I basically just have some constant times epsilon plus my best S-term approximation in the L1 norm divided by square root of x. Okay, so that's good. We had a lot of L1 norm today, a lot of descent vectors, a lot of triangle inequality. That's all done with, right? So we've sort of, I decided to devote today to kind of at least, explaining in full why L1 norm is a good idea for recovering sparse vectors. We did that in two different ways. First we took one approach, which was, using duality theory and trying to construct a dual certificate, which gave us a guarantee about X naught. And like that, what did that depend on? It depended on, the sort of size of the support of X and the sign sequence on the support. And then we had this kind of other line of argumentation, which was even more geometrical, where we said, okay, let's make a very strong assumption about our matrix, that it has this sort of restricted isometry property, that it keeps S-sparse vectors separated from one another. And then really, again, just using geometrical arguments and the triangle inequality a bunch of times, and this restricted isometry property, we have that, like, not only does, this fact that phi keeps S-sparse vectors separate, not only does that mean we can recover X naught, it also means the recovery is stable, in like as many different ways as you can think of. Right? So we have all these different stability results. Okay, that's good. So in my view, since this is kind of like, I view this segment of the course as kind of like an introduction to the mathematics of compressed sensing, there's only one kind of gap left. And that's like, all of this was predicated on the fact that, that this was true for your matrix. So what I want to do for our first lecture tomorrow is, show that this is true for a random matrix phi. And it's going to be, the lecture, the ideas we use there are going to be very different than the ideas we talked about today. So it's really going to be all about like probability and adding together random variables. But again, it'll be kind of the same level of difficulty in that, like, actually, I think it's even easier in a sense that, what you need to, at the end of the day, all you really need is a basic understanding of probability theory. And it's just sort of putting a bunch of steps together in the right way. And actually, in this case, kind of unlike what we talked about today, what we'll talk about tomorrow is the little steps, they also are kind of interesting in and of themselves. Even as we're, using them as a means to achieve a greater end. Right? And so then you'll kind of, after we finish with that lecture tomorrow, you'll kind of have like a real sort of power mathematics. You'll know, okay, why do random matrices keep sparse signals separated? And then how does the fact that a matrix keeps sparse signals separated result in, the fact that I can recover them with L1 minimization? All right, so that's great. I'll end it there. Let me just say one last comment, just reiterate that these guarantees, there are similar guarantees for other algorithms too, doing things like iterative hard thresholding or other types of 3D algorithms. A lot of the ideas we used in this line of argumentation also come up when you analyze those algorithms as well. So, even if you're interested in those, this isn't a waste of time. So, yeah. All right. I'll end there, and we'll see you guys again tomorrow.